Welcome to White Space. We asked how big life can get. The answer might be the universe itself. Put this on in the background, close your eyes if you want, and let the story carry you. There is a question that sounds simple until you sit with it long enough to feel its weight. How big can life get? Not life as a metaphor, not life as a spiritual concept. Life in the strictest scientific sense, an organism, a body, something that eats, grows, reproduces, and eventually dies. What are the actual upper limits? And once we start pulling that thread, something unexpected happens. The question of maximum size transforms quietly and inevitably into a far more unsettling question: is the universe itself alive? We are going to follow that thread all the way. Let us start on the ground. When we think about large animals, we tend to think in terms of mass and length. Earth has produced some genuinely staggering bodies. Adult male gorillas, the heaviest of our primate relatives, can reach 2 meters in height, a meter across the shoulders, and more than 250 kilograms in weight. It is strongly advisable not to argue with them about anything. African elephants, the largest land animals alive today, reach 7 meters in length, stand 3.5 meters at the shoulder, and can carry up to 12 metric tons on 4 legs without complaint. These are remarkable engineering achievements by evolution. But neither of them is the largest animal that has ever lived on this planet. That title belongs to the blue whale, up to 33 meters long, nearly 200 tons, an animal so massive that its heart alone weighs as much as a small car, and a human child could crawl through its aorta. And here is the first clue. The largest animal on Earth lives in water. This is not coincidence. It is physics. Water counteracts gravity. When a body is submerged, the surrounding fluid supports a significant fraction of its weight, reducing the structural demands on bones and tissue. A blue whale on land would be crushed by its own mass within minutes. The skeleton simply could not bear it. This tells us something fundamental about the relationship between size and environment. To grow large, a body needs either buoyancy or extremely robust internal architecture, or both. For land animals, the constraint is the strength of the skeleton relative to the cube root of body mass. If you take a large animal and scale it up 10 times in every dimension, its mass increases by a factor of 1,000, but the cross-sectional area of its bones, which determines their load-bearing capacity, only increases by a factor of 100. The bones shatter. The body collapses like a bridge built from the wrong materials. Even Galileo Galilei wrote about this in the 17th century. There is a hard ceiling on how large a terrestrial animal can be before its own skeleton becomes its enemy. What about moving to a smaller planet? If you could reduce gravity, you could grow larger bodies. Smaller planets have less mass, and less mass means weaker gravitational pull. In principle, on a planet with 1/10 the mass of Earth, the largest creatures could theoretically be 10 times the size of anything we have here. You could have a gorilla the height of a 5-story building. The physics would allow it. But this only works within a narrow range. A planet less than about 1/10 Earth's mass cannot hold onto an atmosphere. Without atmosphere, complex life as we understand it cannot exist. Our building-sized gorilla starves in vacuum. So terrestrial biology, even on other worlds, has a ceiling. But what about space itself? Remove the planet entirely. Remove gravity as a dominant force. What grows then? Consider a hypothetical organism drifting between stars, something like a vast biological net or a membrane or a structure resembling a living sail. Such a creature could theoretically harvest raw material from interstellar dust clouds, using starlight both for energy and as a means of propulsion. A biological solar sail growing outward in all directions to avoid collapsing under its own gravity. As it grows larger, it might begin to rotate, adding angular momentum, balancing inward gravitational pull against outward centrifugal force. The larger it grows, the faster it spins, the more stable it becomes. Such an organism's only real constraints would be the availability of raw materials and stellar energy. It could, in theory, drift into inhabited star systems and strip resources from asteroid belts and planetary rings like a vast silent tide, then move on, having consumed what it needed. Reproduction might work by fragmentation. When the organism grows beyond a certain size, it simply divides like a cell undergoing mitosis, sending two or more offspring drifting in different directions across the dark. If you're thinking this sounds unsettling, that instinct is worth paying attention to. But let us go further. What about an organism the size of a star system? Here the problem shifts from structural to metabolic. Any living system needs to move energy and materials between its parts. In organisms, we know this is accomplished through blood, sap, electrical impulses, chemical gradients. All of these processes take time. They are limited by the speed at which molecules diffuse, at which signals propagate. For an organism the size of a solar system, with a star as its primary energy source, metabolism would be extraordinarily slow. An internal signal, the biological equivalent of a nerve impulse, would take years, decades, centuries to travel from one part of the body to another. This is not necessarily fatal to the concept. A slow metabolism is still a metabolism, but the organism's ability to respond to its environment would be profoundly sluggish. Predators would be irrelevant. Weather would be irrelevant. Only geological and astronomical timescales would matter. And what about thought? This is where the problem becomes genuinely intractable. Human intelligence depends on the rapid exchange of electrochemical signals between billions of neurons. The speed of this exchange, signals crossing from one side of the brain to the other in milliseconds, is what makes conscious thought possible at the timescales we experience it. Now imagine a brain the size of our galaxy. At the speed of light, a signal from one edge to the other would take 100,000 years. A single thought, in any meaningful sense, would require geological epochs to complete. Since the Milky Way formed, such a brain would have managed perhaps 10,000 complete signal crossings. 10,000 thoughts across the entire history of the galaxy. A philosopher of unimaginable patience, certainly, but also almost certainly not what we would recognize as a mind. This brings us to the problem of cooling. Every computation, biological or electronic, generates heat. In small organisms, the surface area of the skin is sufficient to radiate away the heat generated by metabolism. But as organisms scale up, their volume grows faster than their surface area. The Swiss biologist Max Kleiber observed in the 1930s that metabolic rate scales with body mass in a remarkably consistent way across nearly all animals, a relationship that prevents large organisms from simply cooking themselves. But there are limits. At a certain mass, even the most optimized metabolic architecture cannot shed heat fast enough to remain functional. By some estimates, the ceiling for a terrestrial mammal based purely on thermal constraints is around 1 million kilograms, less than 10 times the mass of a blue whale. Beyond that, the structural problem overtakes the thermal one anyway. The body becomes its own obstacle, and yet there is one more idea worth sitting with before we leave this territory. There exists a theory, not mainstream science, but not entirely without support, that the universe itself exhibits the hallmarks of a living system. It grows, it has a metabolism of sorts, with energy flowing from high-density regions into low. It produces complexity from simplicity over time. It began in what might be called a birth event and will, according to most models, eventually reach a state of maximum entropy that resembles death. Our understanding of these changes as we make new discoveries in quantum mechanics, cosmology, and astrobiology. The boundaries of what we call life may not be as fixed as we assume, and the question of whether the universe satisfies those criteria is not ultimately a question we can yet answer. It is, however, a question we should not dismiss. We will return to it. For now, let us go somewhere closer to home. The field of astrobiology, the scientific study of life's potential beyond Earth, approaches this question methodically. It examines what conditions are necessary for life to arise and persist, then asks where those conditions might be found. The starting point is always our own solar system. Not because it is the most interesting region of the cosmos, but because it is the only one we can currently reach. And what we have found there in the past few decades has been genuinely surprising. Begin with Mercury, the innermost planet. Half of its surface faces the sun and bakes at temperatures exceeding 400 degrees Celsius. The other half faces permanent darkness and freezes to nearly -200. There is no atmosphere worth mentioning, no liquid water, no magnetic field to deflect radiation. If there is life on Mercury, it would have to exist deep on the ground in conditions so extreme that even our most resilient known organisms would struggle to survive. The probability is low. It is not zero, but it is low. Venus is more interesting and more tragic. In many ways, Venus is Earth's twin, similar size, similar composition, similar distance from the Sun at formation. Early in its history, it may have had oceans and a temperate surface. The conditions for life may have existed there. Then something went wrong. A runaway greenhouse effect, likely triggered by increased volcanic activity, evaporated the oceans and drove surface temperatures above 450 degrees Celsius. Lead melts at those temperatures. The atmospheric pressure at the surface is 90 times that of Earth's at sea level. Nothing we know of can survive on the Venusian surface. But the upper atmosphere is another matter. In 2020, astronomers reported the detection of phosphine in Venus's cloud layers, roughly 50 to 60 kilometers above the surface. This is significant because phosphine, a molecule made of phosphorus and 3 hydrogen atoms, is chemically unstable under Venusian conditions. It should break down rapidly. Something must be continuously producing it. On Earth, phosphine is produced in meaningful quantities by only one natural process, the metabolism of anaerobic bacteria. In oxygen-free environments, certain microbes generate phosphine as a byproduct. Could something similar be happening in the Venusian clouds? The pressure there is closer to Earth's surface pressure. The temperature is roughly 70 degrees Celsius. Hot, but not impossibly hot. Some thermophilic bacteria on Earth thrive at similar temperatures. The detection remains contested. Some researchers argue it could have an abiotic origin, perhaps volcanic outgassing or unusual atmospheric chemistry. Phosphine can also be produced by lightning under certain conditions, but the detection itself has not been convincingly explained away. It sits in the literature as an unresolved question. In science, unresolved questions are among the most valuable things we have. Mars draws more attention, partly because it is closer, partly because its history is more legible. Orbital surveys and rovers have confirmed that Mars was once wet. There were rivers, there were lakes. There may have been a shallow ocean covering much of the northern hemisphere. The evidence for this is written in the geology: dried riverbeds, mineral deposits that form only in the presence of liquid water, sedimentary layers laid down over millions of years of flowing streams. Mars was once, at least partially, a world where life as we understand it could have existed. Then the planet's interior cooled. the magnetic field weakened and eventually collapsed. Without that magnetic shield, the solar wind stripped away most of the atmosphere over hundreds of millions of years. The surface became cold, dry, and flooded with ultraviolet radiation. Whatever was on the surface, if anything was there, would have had to move underground to survive, which makes what has been found in the Martian atmosphere particularly interesting: methane. Seasonal fluctuations in atmospheric methane detected by orbiting spacecraft and confirmed by surface rovers. On Earth, the vast majority of atmospheric methane comes from biology, from the metabolic processes of microbes and larger animals. Methane can also be produced geologically through the reaction of water with certain rocks at high temperatures, a process called serpentinization. On Mars, either explanation is plausible, but neither has been confirmed, and the seasonal variation is suggestive of an active source rather than a one-time geological event. The Curiosity rover found organic molecules, thiophene derivatives, among others, preserved in 3 billion-year-old sedimentary rock. On Earth, thiophenes are found in coal and crude oil, both products of biological processes over geological time. They can also form through abiotic chemistry. The finding does not prove past life on Mars. It does prove that Mars was once chemically complex enough that life would not have been impossible. Future missions may give us better answers. A drill capable of reaching 2 meters below the surface could access material shielded from radiation, where biosignatures might still be preserved. The search continues beyond Mars. The solar system becomes unexpectedly hospitable. Europa is a moon of Jupiter. On the surface it looks lifeless, a smooth, cracked sphere of ice, with almost no atmosphere, bombarded by radiation from Jupiter's magnetic field. But beneath that ice lies an ocean, not a frozen lake, a global ocean of liquid water, kept liquid by the tidal flexing of Europa's interior as Jupiter's gravity constantly kneads and heats the moon. This ocean is estimated to contain more water than all of Earth's oceans combined. And at the bottom of that ocean, where water meets rock, there are almost certainly hydrothermal vents, places where chemically rich water circulates through the seafloor, driven by the same tidal heating that keeps the ocean liquid above. On Earth, hydrothermal vents support entire ecosystems that owe nothing to sunlight. Bacteria, tube worms, crabs, shrimp, all living on chemical energy derived from the interaction between hot water and rock. This ecosystem type is called chemolithotrophy, life fed by geology. If the same process operates on Europa, and the chemistry strongly suggests it does, then the basic requirements for complex ecosystems may already be in place in that dark ocean, 400 million miles from the Sun. 2 other Jovian moons, Ganymede and Callisto, also show evidence of subsurface oceans, though these may be sandwiched between layers of ice in ways that reduce direct contact between water and rock, and therefore reduce the chemical exchange that life needs. Europa appears to be the best candidate. Enceladus, a moon of Saturn, may be even more compelling. Enceladus is small, only about 500 kilometers across. But it has something no other body in the solar system has: geysers. Plumes of water vapor and ice particles erupting from cracks near the South Pole, shooting hundreds of kilometers into space. The Cassini spacecraft flew through these plumes and sampled them directly. It found water, carbon dioxide, methane, hydrogen, molecular nitrogen, and complex organic molecules. It found silica nanoparticles, which form only when liquid water interacts with rock at temperatures above 90 degrees Celsius. This is direct evidence of hydrothermal activity in Enceladus's subsurface ocean. The hydrogen in particular is significant. On Earth, hydrogen produced by hydrothermal vents provides energy for methanogenic archaea, microbes that combine hydrogen with carbon dioxide to produce methane and water. The same chemistry that feeds life in Earth's deep ocean appears to be available right now in the ocean of Enceladus. If you wanted to design a test for the conditions necessary for microbial life to arise, and then build a real-world example of those conditions somewhere accessible, you might design something very much like Enceladus. Titan, Saturn's largest moon, is different in kind rather than degree. Titan has a thick atmosphere dominated by nitrogen just as Earth's is. It has clouds, rain, rivers, and seas. There is a complete hydrological cycle: evaporation, condensation, precipitation, surface flow. But the working fluid is not water, it is methane. The rivers run with liquid methane. The seas are made of ethane and methane at temperatures around -179 degrees Celsius. And beneath the surface, separate from all of this, there is evidence of a liquid water ocean, but deep down, insulated from the chemistry at the surface. The possibility this raises is not conventional life. It is something else entirely. The organic chemistry on Titan's surface is extraordinarily complex. Tholins, prebiotic molecules, carbon, nitrogen compounds that have not yet been fully catalogued. If something could survive in liquid methane using hydrocarbon chemistry instead of aqueous chemistry, it would be so alien to our current biology that we might not recognize it as life at first encounter. It would process acetylene for energy the way we metabolize glucose. It would breathe hydrogen the way we breathe oxygen. Its biochemistry would violate every assumption we have built into our search instruments. Titan is scheduled for exploration. The Dragonfly mission, a nuclear-powered rotorcraft lander, will arrive in the 2030s and conduct the first aerial survey of any moon other than Earth's. What it finds may force a revision of our definition of life. For now, there is only one place in the known universe where life has been confirmed: the planet you are sitting on. But the more we study our solar system, the more it looks like that loneliness may be temporary. One hypothesis offers a bridge between that loneliness and potential company. Panspermia is the idea that life, or at least the building blocks and seeds of life, can travel between worlds through space. This is not a fringe idea. It is taken seriously enough by the scientific community that dedicated experiments have been conducted aboard the International Space Station to test it. The experiment, named BioRisk, placed a variety of organisms outside the station, exposed to vacuum, radiation, temperature extremes, and the full hostility of open space for approximately 1 year. The subjects included bacterial spores, fungal spores, insect larvae, plant seeds, and crustacean eggs. When the experiment concluded and the samples were retrieved, the results were startling. Most had survived. Larval mosquitoes showed an approximately 80% survival and recovery rate. The organisms had endured conditions that should, by every reasonable expectation, have been lethal. A separate experiment collected samples from the outer surface of the station's hull and analyzed them for biological contamination. Researchers found marine plankton, organisms that have no conceivable mechanism for reaching orbital altitude through normal dispersal. The most plausible explanation involves what researchers call the ionospheric lift, extremely fine biological material, including spores and microbial fragments, carried upward by atmospheric electrical gradients to altitudes far above the troposphere. This suggests that planetary surfaces leak biology into space. Not easily and not in large quantities, but measurably. If an asteroid strikes a life-bearing planet with sufficient force, it can eject material into space, material that contains living microbes or preserved organic compounds. That material can drift for millions of years before being captured by another planet's gravity. The question is not whether this kind of transfer is physically possible. We know it is. The question is whether anything survives the journey and establishes itself in the new environment. There is no confirmed example of panspermia in our solar system, but we have not looked hard enough yet. The organic molecules in Martian rock, the chemistry of comets, the prebiotic complexity of Titan, all of these are consistent with a solar system in which biology, once started somewhere, could have seeded itself elsewhere. We hold that thought and step back. Centuries of astronomy have brought us to a place of uncomfortable knowledge. We know the universe is vast beyond any intuitive grasp. We know it is old, 13.8 billion years old. We know it contains at least 2 trillion galaxies, each containing hundreds of billions to trillions of stars, and that most of those stars have planets. We know that the chemical elements necessary for life as we understand it, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, are among the most common elements in the cosmos. They were forged in the cores of stars and distributed by supernovae across every corner of the visible universe. Given all of this, the silence is puzzling. Enrico Fermi asked the question in 1950, simply and directly. Where is everybody? This became the Fermi paradox. If the conditions for intelligent life are common, and if civilizations persist and expand once they arise, we should by now be seeing some evidence of them. Radio signals, megastructures, the systematic transformation of resources on an astronomical scale. Anything. Instead, silence. There are many proposed resolutions. In 1961, astronomer Frank Drake formalized the variables involved in estimating the number of communicating civilizations in our galaxy. His equation multiplied together estimates of the rate of star formation, the fraction of stars with planets, the fraction of those planets capable of supporting life, the fraction where life actually arises, the fraction where intelligence develops, the fraction of intelligent species that develop communications technology, and the length of time such civilizations survive in a communicating state. The equation itself is not controversial. The debate is entirely about the values to plug into it. Estimates of the final result range from essentially 0 to millions, depending on your assumptions. The key variable is the last one. How long do civilizations last? Any civilization that becomes technologically advanced faces a gauntlet of potential extinction events. Nuclear conflict, ecological collapse, engineered pathogens, climate destabilization, asteroid impact. If most civilizations self-destruct within a few thousand years of reaching radio-capable technology, the galaxy could be full of the ruins of intelligence without ever having 2 civilizations alive and communicating at the same time. Our own species is, by any reasonable assessment, somewhere in the middle of that gauntlet right now. In 1964, Soviet astrophysicist Nikolai Kardashev proposed a different way of thinking about civilizations, not by their longevity, but by their energy use. A Type I civilization on the Kardashev scale has mastered all the energy available on its home planet. A Type II civilization has extended that mastery to its host star, capturing and using a significant fraction of total stellar output, perhaps through something like a Dyson sphere, a structure that partially surrounds a star to collect its energy. A Type III civilization commands the energy of an entire galaxy. Carl Sagan estimated that human civilization, as of the late 20th century, was at approximately 0.7 on the Kardashev scale. Not yet a Type F. At our current rate of energy consumption growth, we could reach Type F status within a few centuries. Type II would require millennia. Type III is almost incomprehensible from our current vantage. A civilization at Type III would have had hundreds of millions of years to colonize its galaxy. It would have the ability to restructure star systems, dismantle and reassemble planets, redirect stellar energy on a civilizational scale. We would not need to receive a radio signal from such a civilization to detect it. We would see its engineering in the structure of galaxies, the systematic rearrangement of stellar matter, the uniform harvesting of available energy, the unmistakable signature of deliberate design at an astronomical scale. We see none of that, which means either civilizations like this do not exist, or they have found ways to be invisible, or something happens to prevent any civilization from reaching that scale. The hypothesis known as the zoo theory proposes that advanced civilizations do exist, are aware of us, and have collectively agreed not to interfere. They watch, they wait, perhaps for us to reach some threshold of maturity before initiating contact. Perhaps out of something analogous to the ethical restraints that prevent us from disrupting uncontacted human tribes. Perhaps for reasons we cannot currently conceive. There is another theory, grimmer and more elegant, that has gained traction since its popularization in Chinese science fiction writer Liu Cixin's work. The dark forest theory. The logic is this: every civilization, in order to survive, must expand. Expansion requires resources. Resources are finite. This means that ultimately every civilization is in competition with every other. Now, you cannot know in advance whether a civilization you encounter is hostile or benign. You cannot verify their intentions. Given that you cannot afford to be wrong about this, if you extend trust to a civilization that turns out to be hostile, you may cease to exist. The rational strategy is to eliminate any potential competitor the moment it is detected, before it can grow strong enough to threaten you. The universe in this model is a dark forest. Every civilization moves silently, revealing as little as possible. Any civilization that broadcasts its location has made a catastrophic error. The silence of the cosmos is not emptiness, it is camouflage. Every civilization that ever existed learned or was destroyed before learning that silence is survival. Under the dark forest theory, humanity has been broadcasting for over a century. We have sent intentional signals toward selected stars. We have attached plaques to spacecraft launched beyond the solar system, describing our location, our biology, our mathematics. If the dark forest hypothesis is correct, we have been advertising our presence to hunters. This is a deeply uncomfortable idea. It cannot be dismissed as pure speculation. It rests on a consistent set of premises about the nature of resource scarcity and the impossibility of verifying intent across interstellar distances. Whether it is true depends on assumptions about the psychology and motivation of entities we have never met. But it provides a logically coherent answer to Fermi's question. Let us hold both possibilities simultaneously, that we may be alone and that we may be watched. In either case, the question of what other life might look like if it exists is worth examining carefully. Xenobiology, sometimes called speculative biology, is the scientific discipline that asks what life might look like if the constraints were different. It is not science fiction. It uses real biology, real chemistry, and real physics, and then asks, given these rules, what other configurations are possible? The life we know is built on carbon. Carbon is a remarkable element. It forms stable bonds with itself and with hydrogen, nitrogen, oxygen, sulfur, and phosphorus in an almost unlimited variety of configurations. The complexity of organic chemistry, the diversity of proteins, nucleic acids, lipids, carbohydrates is a direct consequence of carbon's bonding versatility. Life, as we know it, is a particular expression of carbon chemistry in liquid water. But carbon is not the only element with these properties. Silicon sits directly below carbon on the periodic table. It has the same valence electron configuration, the same ability to form 4 bonds. In theory, silicon could serve as the backbone for complex molecules. In practice, silicon-based chemistry faces significant obstacles. Silicon bonds are larger and less stable than carbon bonds at room temperature. Silicon does not form the equivalent of carbon dioxide when oxidized. It forms silicon dioxide, a solid crystal. This is the equivalent of every metabolic breath, producing not a gas you can exhale, but a stone you must somehow excrete. The chemistry works, but it works differently, and it works best at temperatures far above what liquid water tolerates. A silicon-based organism might be most at home in environments that are simply too hot for carbon chemistry, on a world like Venus before the runaway greenhouse, or on a planet orbiting a star cooler and dimmer than our Sun, where geological heat dominates over stellar irradiation. It would probably look nothing like any organism we know. Its biochemistry would be built around different reactions, different energy sources, different structural materials. We might not recognize it as alive. Ammonia is another candidate solvent, replacing water as the medium in which biochemistry occurs. Ammonia remains liquid at temperatures well below water's freezing point, down to about -78 degrees Celsius at standard pressure. An ammonia-based biosphere would be at home in the outer solar system, on worlds like Titan or on the icy moons of Uranus. The chemistry would be slower, low temperatures reduce reaction rates. But slower does not mean impossible. Such organisms might be extraordinarily long-lived, metabolizing at a glacial pace across geological timescales. Sulfur presents yet another possibility on Earth. Sulfur already plays a central role in biochemistry, in proteins, in enzyme function, in energy metabolism. On Io, Jupiter's volcanic moon, sulfur is deposited across the surface in extraordinary quantities by active volcanoes. Hypothetical Ionian organisms might breathe sulfur compounds to rebreathe oxygen, using the reduction of sulfur dioxide as their primary energy source. The radiation environment of Io's position within Jupiter's magnetic field is lethal by our standards. But some of the hardiest known organisms on Earth, the extremophilic archaea found near deep-sea hydrothermal vents, survive conditions nearly as extreme. The gap between what we think life can tolerate and what it actually can tolerate has been narrowing steadily for decades. Then there are concepts so far outside our biochemical assumptions that they barely fit within our conceptual vocabulary. Plasma-based life, organized by electromagnetic fields rather than chemistry. Organisms that persist as self-sustaining patterns in the solar wind. Intelligence distributed across a molecular cloud, thinking in chemical gradients rather than electrical impulses. None of these are supported by evidence. All of them are consistent with the known laws of physics, in the sense that no known law explicitly forbids them. The challenge is not imagining them. The challenge is knowing how to look for them. Carl Sagan wrote that imagination takes us to worlds that never were. But without it, we go nowhere. Xenobiology keeps the search honest by forcing us to confront the limits of our assumptions. The organisms we are most likely to find may not be recognizable as life when we encounter them for the first time. If we are not prepared for that possibility, we might look directly at something alive and walk past it. For decades, certain questions in this domain have stayed in the realm of speculation. Then occasionally something changes. In recent years, the question of unidentified aerial phenomena has undergone a quiet transformation. What was once the domain of enthusiasts and tabloids has moved, with increasing speed, into congressional hearing rooms and institutional research programs. The history is long and complicated. In July 1947, a farmer in New Mexico reported finding unusual debris on his land after a severe thunderstorm, material that he described as unlike anything he had seen before. The military initially confirmed the recovery of something unusual, then retracted the statement, attributing the debris to a weather balloon. The incident in Roswell entered popular mythology. For 30 years, nothing more was said officially. Then, in the late 1970s, an intelligence officer involved in the original recovery gave an interview contradicting the official account, describing materials that resisted cutting and returned to their original shape after deformation. The military subsequently attributed the debris to a classified high-altitude surveillance balloon program. Most people who have looked carefully at the evidence believe that something happened at Roswell in 1947 that has not been fully disclosed. What that something was remains unresolved. Beginning in 1947 and continuing until 1970, the United States Air Force maintained a systematic effort called Project Blue Book to collect and categorize reports of unidentified flying objects. Over its operational life, the project accumulated more than 12,000 reports. The majority were explained misidentified aircraft, weather balloons, astronomical phenomena, optical illusions, but the residual category, roughly 6% of total reports, resisted explanation and was classified simply as unknown. The Soviet Union conducted parallel research, though with less public transparency. Soviet intelligence services treated all UAP reports as potentially significant from a military standpoint. Russian archives from this period remain partially inaccessible, though accounts suggest a systematic collection effort that extended well into the Cold War. In 1990, something happened in Belgium that made quiet skepticism harder to maintain. On the night of March 30th, radar stations at NATO's Air Operations Center tracked multiple unusual objects over northeastern Belgium. Ground observers numbered in the thousands. Eventually, over 13,000 confirmed witnesses, with roughly 2,600 filing detailed written reports. Belgian Air Force F-16 interceptors were scrambled to investigate. Over the course of approximately an hour, the aircraft attempted 9 radar lock-ons. 3 succeeded briefly. In each case, before weapon systems could engage, the target changed position and speed in ways that were difficult to attribute to any known aircraft, accelerating from 240 km per hour to over 1,700 in seconds, dropping from 2,700 meters altitude to 1,500 and back to 3,300 within the same maneuver sequence. No sonic boom was recorded despite apparent supersonic transitions. The Belgian Air Force subsequently released a detailed, unclassified report of the incident. The report was notable for what it did not claim. It did not say the objects were extraterrestrial. It said clearly that the radar contacts were real, that their flight characteristics were outside the known performance envelope of any aircraft in operation, and that no satisfactory conventional explanation had been found. The Belgian case stands as one of the most rigorously documented UAP events on record precisely because the military involved chose transparency over concealment. Fast forward to the early 2020s. Following the public release of declassified video footage by the United States Department of Defense showing Navy aircraft tracking objects with unusual flight characteristics, no visible propulsion, no control surfaces, behavior inconsistent with known atmospheric phenomena, the conversation shifted. In 2022, NASA announced the formation of an independent research team to apply scientific methodology to the study of what was now officially termed unexplained anomalous phenomena, or UAP. The same year, the US intelligence community reported receiving 510 UAP reports over the preceding 15 months, compared to 344 reports over the entire previous 17 years of observation. The volume of incidents had increased dramatically, in part because radar and sensor systems had improved, in part because the stigma of reporting had decreased. Congressional testimony in 2023 included statements from former military and intelligence personnel claiming personal knowledge of non-human origin craft and biological material. These claims were made under oath. They have not been corroborated by physical evidence made available to the public. They have also not been convincingly refuted. The space between those two conditions, unverified and unrefuted, is where the most significant questions about UAP currently reside. There is, however, a competing hypothesis that explains a great deal without invoking extraterrestrial intelligence. Since the 1950s, military research programs on both sides of the Cold War have pursued unconventional propulsion and flight technologies under intense secrecy. A disc-shaped aircraft called the Avocar was publicly developed by a Canadian company for the US military in the late 1950s, intended to achieve vertical takeoff and supersonic flight using a central reaction engine. In practice, the prototype never exceeded 56 kilometers per hour and could not rise more than a few meters. It was officially cancelled. The key word is officially. Consider what 7 decades of classified development might produce, funded by the largest military budgets in human history, staffed by the most capable aerospace engineers of multiple generations, operating in complete secrecy. Technologies that to an outside observer would appear impossible, vehicles that leave no thermal signature, propulsion systems that produce no acoustic shock wave, flight profiles that seem to violate inertia. These would all be extraordinary achievements. They would not require extraterrestrial engineering. Whether such programs exist and whether they account for the full range of documented UAP behavior is genuinely unknown. What is clear is that the phenomena are real. They appear on multiple independent sensor systems, are observed by credentialed professional observers, and behave in ways that current public knowledge cannot explain. The explanation, whether human, non-human, or something more complex, remains to be determined. Truth, as someone once observed, tends to be somewhere nearby. Let us return now to the larger picture and to a concept that ties several threads together. In 1906, at a country fair in Plymouth, England, a scientist named Francis Galton ran an experiment that would trouble him for the rest of his life. Galton had spent decades studying human intelligence and the differences between individuals. He was a proponent of the idea that expertise was rare, that most people were poor judges of complex questions, and that civilization was best served by deferring to those whose demonstrated ability placed them above the average. At the fair, as an entertainment, visitors were invited to guess the weight of a large ox on display. Prizes would be awarded to the most accurate estimates. About 800 people participated. After the fair, Galton collected the tickets and calculated the median estimate. It was 542.9 kilograms. The actual weight of the ox was 543.4 kilograms. The crowd collectively was closer to the truth than any individual expert who had participated. A random sample of fairgoers outperformed the butchers and the cattle breeders. Galton called this remarkable and revised his views accordingly. The phenomenon, studied extensively since, has come to be called collective intelligence, the emergent property of groups that allows their aggregate judgments to exceed the accuracy of even their most expert members. It requires 2 conditions. First, diversity participants must bring genuinely different perspectives based on different knowledge and experience. Second, independence. Each participant must form their judgment without being influenced by the judgments of others. When these conditions are met, errors that are idiosyncratic to individuals cancel each other out, and the underlying truth becomes visible. This phenomenon is not unique to human civilization. It appears throughout biology. Ant colonies solve optimization problems, finding the shortest path between 2 points, allocating labor across tasks of different urgency that would require sophisticated computation if approached by any individual. No single ant coordinates these outcomes. They emerge from simple local interactions following simple local rules. The colony is smarter than any of its members. Microbial biofilms communities of bacteria sharing resources and chemical signals collectively regulate their behavior in response to environmental conditions in ways that no single bacterium could accomplish. They differentiate into specialized roles, they coordinate the timing of attacks on host immune defenses, they exchange genetic material to share adaptations across the community. The term microbial intelligence is not metaphorical. It describes measurable adaptive behavior that exceeds what any individual cell could exhibit. Neurons do this too. No single neuron in the human brain is conscious. consciousness. If that word means anything, is a property that emerges from the interaction of many billions of neurons, none of which has any awareness of the whole they constitute. The whole is not merely the sum of its parts. The parts create something that neither has nor could have individually. Aristotle observed in the 4th century BCE that when many people come together, their collective wisdom may exceed that of any single expert among them. Not because each person is wise, but because each person contributes something that the others lack. He was describing 23 centuries before the modern terminology, the same phenomenon Galton encountered at the Plymouth Fair. Now scale this up. A sufficiently large and diverse network of conscious entities, deeply enough interconnected, might exhibit emergent properties that none of its components possesses. This is not a mystical claim. It is an extrapolation from patterns already observed in biology, from neurons to ant colonies to human societies. As networks grow larger and more densely connected, the emergent behaviors they can produce become qualitatively different from anything achievable by smaller networks. At what scale does the emergent behavior of a sufficiently connected network of intelligent beings become something we would recognize as a new kind of mind? We do not know. We have never had a network of sufficient scale to test the question, which brings us finally back to the cosmos. In the late 20th century, surveys of the large-scale structure of the universe produced an image that surprised almost everyone who saw it. Astronomers had expected the universe to be roughly uniform at large scales, matter distributed more or less evenly throughout space, with local concentrations here and there. What they found instead was architecture. Galaxies are not distributed randomly. They are concentrated in vast sheets and filaments, thin walls of matter that curve and intersect across hundreds of millions of light years. Between these walls lie enormous voids, regions where almost nothing exists. Not just no galaxies, but near total absence of gas and dust as well. The walls and voids together form a structure that resembles, in 3 dimensions, an enormous foam or a collection of soap bubbles packed together. The galaxies are concentrated at the intersections of bubble walls. Inside the bubbles, nothing. This structure has a characteristic scale. The typical diameter of a void is somewhere between 100 and 300 million light years. The universe, at its largest accessible scales, is organized into cells of this size, separated by near-empty boundaries. Physicists have explanations for why this structure formed. In the early universe, quantum fluctuations created tiny overdensities in the distribution of matter. These overdensities attracted more matter, growing over billions of years into the walls and filaments we see today. The cellular structure is, according to standard cosmology, the gravitational imprint of quantum randomness amplified across deep time. But there is a separate observation that refuses easy explanation. Hexagonal structures appear throughout nature at every scale where we look. The columns of basalt formed when lava cools and contracts, the cells of a honeybee's comb, the compound eye of a trilobite, snowflakes, seen under sufficient magnification, benzene rings, Saturn's North Polar Storm, a hexagonal jet stream tens of thousands of kilometers across, stable for at least 4 decades of observation, for reasons that fluid dynamics alone cannot fully account for. Why hexagons? In 2 dimensions, a hexagonal tessellation is the most efficient way to partition a plane into equal areas using the minimum total boundary length. Soap bubbles left to equilibrate form hexagonal cells, for this reason pure geometry minimizing surface energy. Evolution converges on hexagonal structures in biology for the same reason: structural efficiency. In physics, certain crystallographic arrangements favor hexagonal symmetry because they represent the minimum energy state of certain atomic interactions. but the persistence of hexagonal symmetry across such an enormous range of scales, from molecular bonds to planetary weather systems to the large-scale structure of the universe, has led some researchers to suggest it may reflect something deeper. Not just the result of different physical processes arriving at the same efficient geometry, but the fundamental property of space itself at some level below what our current instruments can probe. The suggestion at its most speculative is this, that the fabric of space has a preferred structure, a geometry at the subquantum scale that expresses itself as hexagonal symmetry wherever matter is free to organize itself. This is not mainstream physics. It is a hypothesis in the philosophical sense. But it connects to something mainstream physicists take very seriously, the fine-tuning problem. The laws of physics are described by a set of fundamental constants, the gravitational constant, the electromagnetic coupling constant, the masses of elementary particles, the cosmological constant. These numbers are not derived from more fundamental principles, they are simply measured. And when we ask what would happen if these numbers were slightly different, the calculations are not difficult. The answer is consistently the same. The universe would not support complexity. Increase the strong nuclear force slightly and protons bind together without neutrons, creating a universe with no hydrogen, no stars, no chemistry, no life. Increase gravity by a small factor and stars burn through their fuel in thousands of years rather than billions, leaving no time for planetary systems to form and stabilize. Weaken the weak nuclear force even a little, and supernovae fail to explode, trapping the heavy elements forged in stellar cores and leaving the universe stripped of the atoms that make rocky planets and organic chemistry possible. The numbers we measure are not just compatible with complexity. They appear in multiple independent directions to be positioned precisely at the boundary conditions that allow complexity to exist at all. This is what physicists mean by fine-tuning. Not that the laws of physics were designed. There are several physically rigorous explanations for why the constants might have the values they do, but that the values they happen to have are, by any naive assessment of probabilities, startlingly conducive to the existence of observers capable of measuring them. This observation has not been fully explained. It is one of the open problems in fundamental physics. It sits alongside the origin of the universe, the nature of dark energy, and the resolution of quantum mechanics with general relativity as a question without a satisfying answer. Some propose the multiverse, an ensemble of universes with different constants, most of which are empty or short-lived. And we find ourselves in one that supports complexity simply because any observer must, by definition, exist in a universe that supports observers. This is the anthropic principle, and it is logically impeccable and deeply unsatisfying in equal measure. Others propose that the constants are constrained by some deeper structure of mathematics that we have not yet discovered, that the specific values of the constants are the only values consistent with a logically self-consistent physical theory. This is what some physicists mean when they speak of a final theory. Not that the universe is designed, but that the space of possible consistent universes is far smaller than it appears, and that we necessarily occupy a universe at the interior of that narrow space, and some propose what might be called cosmic selection. The physicist Lee Smolin suggested in the 1990s that universes reproduce through black holes, with each new universe having slightly different constants, an evolutionary process at the cosmological scale. Universes that produce black holes produce offspring universes. The constants in our universe happen to be highly favorable for black hole production, which is also incidentally highly favorable for the formation of long-lived stars and planetary systems. Natural selection extended to the metacosmological scale. None of these proposals is verified. All of them are serious ideas held by serious scientists. We began with the question of how large a body can be. we end somewhere considerably larger. The universe shows signs of organization, a cellular structure at the largest accessible scales, a set of physical constants fine-tuned for complexity, an emergent tendency toward hexagonal geometry at every scale we have examined. It grows, it processes energy, it produces increasing complexity over time. It appears to have begun in something like a birth event and will end in something like a death. The hypothesis of cosmic consciousness, sometimes called cosmopsychism, holds that consciousness is not exclusively a property of biological brains, but a fundamental feature of sufficiently complex information processing systems. Under this view, the universe is not merely an unconscious backdrop against which life happens. It is itself a system that processes information in ways that, scaled up sufficiently, might constitute a form of awareness that we are not yet equipped to recognize. This is, to be clear, a philosophical position rather than a scientific theory in the current state of knowledge. It is not testable by present means. It cannot be falsified. These are serious deficiencies. But consider what we have learned about collective intelligence. No neuron in your brain is conscious. Yet consciousness emerges from their interaction. No ant in a colony understands the optimization problem the colony is solving. Yet the solution emerges. We know that sufficiently complex interactive systems produce emergent properties that transcend the properties of their components. The universe contains approximately 10 to the 80th atoms. It has been organizing those atoms for 13.8 billion years. It has produced, within that span, creatures capable of asking whether it is conscious. Those creatures are made of the same atoms as everything else. They are, in a straightforward physical sense, the universe perceiving itself. What role does that leave for us? If collective intelligence scales with the size and diversity of the network, then the most expensive possible intelligence would require the most expensive possible network. The universe, fully interconnected, aware of itself across all its scales, from quantum fluctuation to galactic filament, would be, in this framework, the ultimate expression of what mind can be. We do not know if that is what the universe is. We are nowhere near the tools required to answer the question. The technology exists to detect radio signals from nearby star systems. It does not exist to detect the information processing patterns of a cosmos-scale mind, if such a thing exists. What we know is this: we are inside something enormous. We have been here for an eye blink of cosmic time. We have learned in that eye blink that the universe is far more structured than it appears, that the conditions for complexity have been sustained with extraordinary precision across billions of years, and that wherever we look for the conditions necessary for life, we find them. The silence of the cosmos may mean we are alone, it may mean we are watched, it may mean that the question of company is posed at the wrong scale entirely, that we are not inhabitants of a universe that might contain other minds, but components of a universe that itself, in some sense, thinks. We do not yet know how to tell the difference. That is not a failure, it is an invitation.